This is the first of two lectures on heat and thermodynamics, and we'll start this off by talking about temperature. This is a typical, fairly old thermometer. And the way these original thermometers were constructed was that in the thermometer is an alcohol that has a certain expansion, and it's dyed red. And at one end is a fairly large reservoir, and then it's forced into a fairly narrow tube such that when the alcohol expands, it causes it to move in a fairly large distance up the tube. And as the temperature increases, the liquid is then expands and it's forced up into this area where it can be read. So there's a large or significant change in length here can measure a fairly small change in temperature. Now, temperature is defined as the average kinetic energy of the molecules in a substance. The key word there is that it's the average kinetic energy. It is not the total kinetic energy of any particular body or substance. It is the average. Now here we have two substances that start out at an initial temperature and then bend or change temperatures. And it's important to note that the second temperature, shown in B, is higher than the first temperature, T0. The curvature, the two strips are straight when you start together, but then subsequently at higher temperatures, one of the two strips has a greater expansion than the other. And in this case, the blue one has a greater expansion, and this causes the strip to bend to the right. Another means of measuring temperature is using different liquids that have different changes depending on the temperature. This is a strip that's frequently put on the forehead of individuals when we are measuring their temperature. And the way it works is there are 6 squares here, and each square has a different liquid. And each liquid has a different heat sensitivity such that when the temperature is below 95, all of them are black. As the temperature rises, the first square on the left will change color, and then the second square, and then the third square, and so forth. And you read the temperature based on which are not black, or where the interface between black and non-black is. Now normal is 98.6, and so the black substance can be either the third one or the fourth one, depending on where you are exactly in the temperature. Now here is a more modern way of measuring temperature. The way this works is by looking at infrared radiation. You may remember from basic science class that infrared radiation is the radiation of heat. And the more heat that something has, the higher the infrared radiation. And you can measure changes in the infrared radiation, and it measures the temperature based on those changes in color. Something that has a very low heat will be in the blue range, and as it becomes warmer, it gets orange and then yellow. And this is a very modern way of measuring it, and it's also extremely accurate. The thermometers that are used, that are placed in the ear, measure this infrared radiation, and they're more accurate than the alcohol thermometers that were used in the past. Now this shows the relationship between the 3 most common thermometer temperature scales used. The bottom here is Kelvin, the middle is centigrade or Celsius, and the top is Fahrenheit. And over here we have absolute zero. That's the point in Kelvin at which molecular motion ceases. This corresponds to minus 273.15 on the Celsius scale, and minus 459.67 on the Fahrenheit scale. Now water boils at 32 degrees Fahrenheit, 0 degrees Celsius, and 273 degrees Kelvin. And I'm sorry, water freezes. That's what I meant to say. I said boils, but I meant freezes. And it boils at 212 degrees, 100 degrees, and 373 degrees. And you'll notice, and this is shown here, that 5 degrees of Kelvin are the same as 5 degrees of Celsius. However, there's 180 degrees between boiling point and the freezing point, and 100 degrees between the freezing point and the boiling point in Celsius. So there's a 9:5 ratio between Celsius and Fahrenheit. Celsius is the SI unit, System International Units for temperature. Fahrenheit is the units that are used in the United States. And Kelvin, or absolute, is used in scientific calculations because at 0, all motion, molecular motion, stops. So when we look at conversions from one temperature scale to another, the Fahrenheit temperature scale is related to the Celsius temperature scale by the following. If you know the Celsius scale, so you already start at 0, a 0 scale, a scale that starts at 0, then you multiply by this ratio of 9 Fahrenheit to 5 Celsius, and then you have to adjust for the fact that 0 degrees Celsius is the same as 32 degrees Fahrenheit, so you have to add 32 here. Conversely, if you're working the opposite direction, you have to first convert the Fahrenheit reading to a 0 scale by subtracting 32, and then it's 5 Celsius for every 9 Fahrenheit. And so you have to make sure that in this one you do the multiplication first, followed by the addition, and in this one you subtract first, followed by the multiplication. If you do it in the wrong order, you'll get the wrong answer. And then to convert from Celsius to Kelvin, you just add 273. There are no direct conversions from Fahrenheit to Kelvin, so you have to convert first to Celsius and then to Kelvin if you have a Fahrenheit temperature. So let's take a look at some examples. Okay, so let's take a look at this first problem. We have 26.5 degrees Celsius, and we want to convert that to Fahrenheit. So the first thing we have to do is write down our formula. Fahrenheit is equal to 9/5 Celsius plus 32. So that's going to be 9/5 times 26.5 plus 32. And if you do the math here, you should get 79.7 degrees Fahrenheit. So 26.5 degrees Celsius is approximately 79.7 degrees Fahrenheit. Now if you start with a Kelvin term, 421.4 degrees Kelvin, like I said, you can't convert directly from Kelvin to Fahrenheit. So you have to first convert this to Celsius. So Kelvin is equal to Celsius plus 273. So you have to subtract 273 from this number. So C equals 421.4, and I'm just going to say minus 273 rather than 273.15. And if you do that subtraction, you get 148.4 degrees Celsius. Then, again, you put it in this same formula here. So that's going to be 9/5 times 148.4 plus 32 degrees. And when you do that math, you get 267.3 degrees Fahrenheit. So this level of Kelvin is equal to this amount, this level of Celsius and this level of Fahrenheit. Moving down to the bottom, converting from Kelvin to Celsius is actually quite simple. If you have 141.4 degrees Kelvin, Kelvin is equal to Celsius plus 273. So you're going to subtract 273 from this number. So C is equal to 141.4 minus 273. And if you do the math here, you get a negative 132.6 degrees Celsius. The last one is converting a Fahrenheit temperature to a Celsius temperature. And remember that Celsius is equal to 5/9 times the quantity, Fahrenheit minus 32. So you have to start out by subtracting 32. I'm sorry, this is F. You start out by subtracting 32 and then multiplying by this. So it's 5/9 times 96.1 minus 32. And if you do the math here, you get 35.5 degrees Celsius. Let's move on now to talk about thermal expansion. Thermal expansion occurs when a substance is heated and it causes the substance to get bigger in volume, and that can be expressed in terms of a linear change, or in a total volumetric change, or in a change in area. Now here's an example of something that if you stop at a railroad crossing or a bridge, you'll see all the time. These are called expansion joints. And the purpose of these joints is to allow the bridge to expand without causing buckling of the concrete. Thermal expansion, as I said, is a change in size, length, or volume due to a change in temperature. The formula for length, if you're calculating a change in length, is given here. The change in length is equal to a factor called the coefficient of linear expansion times the length, the original length, times the change in temperature. So delta L is equal to the change in length. Alpha is called the coefficient of linear expansion. L is the original length at the original temperature, and delta T is the change in temperature. Now, if the temperature goes down, the length gets smaller, and so it's a negative number. If the temperature goes up, the length gets larger. This formula is a formula that you need to keep in hand. Now, linear expansion can be expanded to take into account either area or volume. And the way to do area is simply to take the linear expansion and multiply it by 2. So for example, if you have a box like this, it's going to linearly expand in the y-axis and linearly expand in the x-axis. And it will also expand in terms of a circle, in terms of the radius. The volume gives you something called beta, which is the coefficients of volumetric expansion. The key to understand here is that this is actually 3 times the coefficient of linear expansion. So you could take this number and multiply by 3 if you wanted to. The linear expansion multiplied by 3. Either way will work. So the change in volume here is equal to the coefficient of volumetric expansion times the original volume times the change in temperature. Or you could do the linear expansion in one dimension, say the x-axis, and then multiply it by 3 to take in the y-axis and the z-axis. Thermal stress is a common cause of problems that you see in the roads, because what happens is there is inadequate preparation and inadequate accounting for the change in size of the concrete or asphalt during times of high and low temperature, and this thermal stress causes the material to crack and break. When we return, we will do some example problems in the area of thermal expansion.